Recording in progress.
All right, so we are getting started. So today we are going to talk about differential amplifiers and try to finish what we started discussing in the last lecture. But before going into the details, on Canvas, I have uploaded the CMOS logic circuits theory for Lab 7 and transmission gates, which is also required for the theory for Lab 7. So I have uploaded these two documents on your Canvas. Also, I have uploaded two videos from last year, and I'm doing this because some of you are getting started with Lab 7 on Monday, but we haven't yet covered the theory portion for Lab 7, which is going to be digital circuits. So if you want to get an idea about that, these videos would help you in terms of what you need to know about CMOS logic circuits and transmission gates. So if you have lab on Monday, for example, so please go through these lectures first before going to the lab. We'll try to cover them starting Monday's lecture or at the latest Wednesday's lecture next week. But I just wanted to post those lectures which are recorded from last year so that you get an idea about what to expect in terms of digital circuits. All right. Now, in terms of differential amplifiers, last day we looked at what are the, or how does a differential amplifier look like, and what would be the voltage swings at the output of the differential amplifier, what would be the conditions for which the transistors will be on and the transistors will be in saturation. And because of that, you already know that the transistor need to be in saturation if it needs to operate as an amplifier. Now, speaking of digital circuits, which you will start next week, and also because of your Lab 7, you will see in digital circuits, the transistors do not need to be in saturation. And that's the basic difference between analog and digital. In analog circuits, we want transistors to be in saturation because we eventually want gain. In digital circuits, you want transistor to operate as a switch, and those two are exclusive of each other. If the transistor operates as an amplifier, it does not operate as a switch. If it operates as a switch, then it doesn't operate as an amplifier. So that's a very fundamental difference between digital and analog. And in all your digital circuit classes, you'll see the professor will be talking about the transistor as a switch, and you don't want the transistor to be in saturation. On the other hand, in any analog circuit related class, where you want your transistor to behave like an amplifier, you want the transistor to be in saturation. So that will be a basic difference. So when I was a student, the first time I took these two classes, I got very confused because in one class, the professor was talking about the fact that the transistor needs to be in saturation. And in another class, the professor talked about that the transistor cannot be in saturation. But both are true because one is digital where your gain is important, and the other one is analog where your gain is important, and the other one is digital where the switching behavior is important. We'll learn more about that next week when we start discussing about the basics of digital circuit. But today I want to discuss a little bit more on differential pairs, which means that we are still discussing amplifiers. We are still in the analog domain, and we still want the transistor to be in saturation. All right. Now, speaking about the transistor being in saturation and being able to operate as an amplifier, we want the small signal gain of the differential amplifier, let's say. Okay, and small signal analysis, by now you'll know that whenever we talk about small signal analysis, we're talking about the AC analysis for the amplifier. And we want to find out what is the AC gain. On the other hand, DC analysis or large signal analysis, that just figures out whether the transistor is in the correct operating region or not. For an amplifier, that correct operating region will be saturation. For a digital circuit, that correct operating region will be either cutoff or triode. Okay, so now if you want to find out the gain of this differential amplifier, you already know that the two inputs of the differential amplifier should look something like this, that you have a sine wave in one of the inputs, and you have the 180-degree phase shifted version of the same sine wave at the other input. Of course, the DC level should be something that makes sure that the transistor M1, as well as the transistor that actually constitutes this current source, all of those transistors are in the saturation region. So your DC level needs to ensure that. And otherwise, the transistor is either not on or not in the saturation region, and you cannot expect the transistor to provide gain in that case. Okay. But that DC is always going to be a common mode, whereas the AC is going to be the differential mode signal input for the amplifier. Now, as you have learned in 3111, that as soon as you are analyzing multiple sources in the circuit, there are multiple voltage sources, one way to take care of it is by applying the superposition principle. And we actually applied the superposition principle when we talked about DC analysis and AC analysis. So when we are doing DC analysis, we don't care about any of the AC voltages or currents, right? Because we are only doing the DC analysis. When you are doing the AC analysis, on the other hand, you don't care about the DC voltages or currents. You assume that those are done, and it is the reason why we do DC analysis and AC analysis are separate. DC analysis, you want to find out whether the transistor is in the correct operating region. AC analysis you're doing when you want to find out what is the gain of the transistor. Okay, but you can do these things separately by using the superposition principle. That, okay, I'll only analyze DC at first, and I'll only analyze AC, assuming that the DC analysis has been done. So you already applied that principle in the class before, but now for a differential pair, for the two AC inputs, you can also do, or you can also utilize the superposition principle, that you first consider only one of the inputs, figure out what is the effect of that, and then consider the other input. Okay. So if you do that, so your method one to analyze this differential pair through superposition principle is that first you set V in 2 to be equal to 0. So the second MOSFET, that AC input is equal to 0. That does not mean it is grounded though. Again, just going back to the same concept again and again, but this ground does not mean it is actual categorical absolute ground. It does not mean that, because it needs to be biased. If this transistor is not biased, it is probably not on. So this is just means that this is an AC ground and not a DC ground necessarily. Right? So V in 2, the AC quantity is equal to 0. The DC could be anything, but we don't care because we are assuming that the DC has been set correctly. We want to find out the effect of V in 1 at point X and point Y. Those are the two outputs of the differential amplifier. Now to find Vx, first note that this M1 transistor forms a common source stage with a degeneration resistance. Why am I saying that there is a degeneration resistance? That is because as I'm trying to do an AC analysis here, the DC current source, remember that this is a DC current source. This is not AC. AC is only applied at the input side. So this DC current source is having an infinite resistance. Right? Any current source has an infinite resistance because ideally any current source should have a parallel resistance. And if this current source is ideal, that parallel resistance is infinity. That means looking down at this current source, you'll always see infinite resistance. So whatever AC voltage you're applying at the input side, this left side branch, that will create an AC current, flowing from drain to source of this transistor. And that entire AC current will flow like this. That entire, let me draw it with a different color, maybe red color, that this entire AC current is flowing like that. The AC current does not go to ground through this path. That does not exist. That cannot happen because this is a DC current source, which means it has an infinite impedance and current cannot flow through an infinite impedance. So current has to go like this through the other transistor. And when that happens, I'm just redrawing it in a different way on this right side graph or in the middle circuit, that you have your V1 over here, you have your M1 transistor. I am getting rid of this ISS current source because that's just a DC, and DC means I can ignore it while I'm doing AC analysis. Okay? Or by ignoring, what I mean is that I'm making sure that that AC current source is open, or the DC current source is open. A DC voltage source, you can make it shorted to ground, or when you're doing AC analysis. It's the same thing that we had done before as well. All right. So now, what do you see looking on this side? Basically, looking down here, you will see infinite impedance. But looking on the right side, the current, if you follow the current path which goes towards the right, and by current path, I mean the AC current path, because again, we are only doing the AC analysis. So you see the source of this M2 transistor, right? You'll see the source of that M2 transistor, and that M2 transistor gate is grounded. This is the drain of the M2 transistor connected to RD2 and then to VDD, which is also AC ground. So effectively, what do I see here? If I again simplify this circuit shown in the center to the circuit that is shown on the right side, you have a V in 1 going to the gate of transistor M1, which is this left side branch transistor. You have RD1 on top. You have Vx at the drain of that transistor. And you have Rs, that is the resistance looking into the source of this M2 transistor as your degeneration resistance connected to the source of the M1 transistor. And now you already know how to solve this. You already know what is the solution for this circuit in terms of AC. So your M1 is forming a common source stage with a degeneration resistance equal to the impedance looking into the source of M2. And that resistance is going to be Rs, that is equal to 1 upon GM2. And of course, we are neglecting channeling modulation and body biasing effect. Those are the two non-idealities that we looked at in the past. So let's say we are neglecting both of them. So the resistance looking into the source is equal to 1 upon GM. Now from this figure C, you can find out what is going to be your Vx, that is this voltage divided by the input voltage. And that, I think you already learned about that this in the past, that this is going to be minus of GMRD divided by 1 plus GMRS. Right? Because remember that the effect of source degeneration is that your GM becomes GM divided by 1 plus GMRS. Now, what is RS and what is GM? GM is basically GM1 because you are only considering the GM of the M1 transistor. That's where your AC input is provided. So GM1 times RD1 divided by 1 plus GM1 times RS, and RS is equal to 1 upon GM2. So basically, I can write that down as GM1 times 1 upon GM2. Now, this is the same equation that is written over here. It's just that you're dividing the numerator and denominator with GM1. So numerator becomes minus RD, denominator becomes 1 upon GM1 plus 1 upon GM2. So this is the same equation that we wrote here. And just by dividing the numerator and denominator with GM1, you get this equation on the left. All right. Now to find out Vy, to find out the voltage at node Y. So previously in the last slide, you found out what is the voltage at node X, or basically what is the ratio of Vx over V in 1. So you can find from that ratio, you can find out what is Vx. To find out Vy, you need to note that M1 drives M2 as a source follower. The M1, this transistor is creating a current, and that current is going into this M2 transistor. Right? So if you just consider this M2 transistor over here and try to find out what is the voltage at the drain of this M2 transistor. So in that case, you'll see that the M2 transistor source has the input coming in. The input comes in at the source of the M2 transistor. And accordingly, you'll create an output for that M2 transistor. Now, if you model that, how would that look like? And if you simplify this left side circuit, it becomes the one shown on the right. That you have a Thevenin equivalent voltage and a Thevenin equivalent resistance, which is given by everything that is on this left side branch. Right? So you have this dotted line on the left side, and that dotted line is the same dotted line over here, which shows the Thevenin equivalent of that left side rectangle, within which you have M1, V1, RD1, and so on. So all of that is represented with the Thevenin equivalent voltage of Vt and a Thevenin equivalent resistance of Rt, which is in series with the voltage source. That is connected to the source of your M2. So that AC current is going into the source of your M2. The gate of your M2 is grounded. This is an AC ground, remember? And then you're looking at the output at the drain terminal. So what kind of a amplifier is this? Your gate is grounded, right? That means it's a common gate. So this is a common gate amplifier. And for that, the input is coming in at the source terminal, output is at the drain, gate is the common terminal. So M1 drives M2 as a source follower and replace V1 and M1 by a Thevenin equivalent. So the Thevenin voltage VT that is available at the source of this M2, how much will that going to be? What is the voltage that is available at this node? Remember that if you think about M1 transistor, you're applying your input at the gate and you want to find out what is available at the source. So what kind of a configuration is that? That is going to be a source follower or a common drain configuration, right? So this is a source follower or a common drain configuration where you're applying your input at the gate terminal and you're looking at the source voltage. The input at gate, output at source. Drain is the reference terminal. That is common drain or source follower. And for source follower, you know that the gain is almost equal to 1. And that is why it is called a source follower. It's that the output is at the source and the output at the source follows the input. That's why it's called a source follower. So the source node of both of these M1 and M2 transistor, the voltage at the source node is going to be equal to V1. And that's basically the Thevenin equivalent voltage that you are getting at the output of this equivalent Thevenin voltage source. Right? You apply V1 at the gate of M1 transistor, you get the same V1 at the source of the M1 transistor, which is the input to M2. So your Vt is equal to V1. What is the Thevenin equivalent resistance? The Thevenin equivalent resistance is the resistance looking into the Thevenin black box, right? So this is the black box that represents the Thevenin equivalent circuit within the dotted rectangle. So what is the resistance looking into that dotted rectangle? Again, you will see the source of the M1 transistor, which means that the Thevenin equivalent resistance looking here is just 1 upon GM1, right? So Thevenin equivalent resistance is 1 upon GM1. That's RT. And Thevenin equivalent voltage is equal to V1 because this is acting like a source follower. Question? If there is no channel length modulation, then RD has no effect. Okay? So we discussed that when we were, so let's go back to this. Maybe. So let's open our MOSFET amplifier cheat sheet. So if you're looking into the source of a transistor, and if the transistor's RO is infinitely large, then you are seeing 1 upon GM. If RO is not infinitely large, then you are going to see RO divided by 1 plus GMR. Even if there is a RD resistance connected, which is the case in this case. So your question was, what is the effect of that RD resistance if I'm looking from the source on the upward side? So if you have that RD resistance, and if your RO is not infinite, then what you're going to see looking from the source terminal looking up is RO plus RD divided by 1 plus GMR. Again, you can prove all of that by just drawing the small signal model of the transistor and finding out how much resistance you're seeing at the source terminal. Now, this is when RO is not equal to infinity. If RO is equal to infinity, just divide the numerator and denominator with RO. So you get 1 plus RD over RO. So that becomes 0. And then in the denominator, you have 1 divided by RO, that is 0 again, plus GM. So how much is that? That's just 1 over GM. So there is absolutely no effect of this RD on that 1 over GM resistance that you're seeing looking from the source if your RO is infinite. If your RO is not infinite, then then you have to do a little bit more complex calculation. But if your RO is infinite, the resistance looking from the source is always going to be 1 upon GM. Okay. So that's why we said that looking here, you always see 1 upon GM. That RD1 has no effect if the lambda of this M1 transistor is equal to 0. So now M2, that this is operating as a common gate stage. And what is the gain of a common gate stage? You know that the gain of the common gate will be, if you are applying this voltage V over here, you can write that down as, or you can basically do all the small signal modeling, and you can find out what is the, or you can figure out what is going to be your gain over here. But I can just write it down as GM2 times RD2 divided by 1 plus GM2 by GM1. And you can prove that from the small signal model once again. So we can, let's just try to do that. I think we have the proof over here. Yes. No, I guess we did not do that, but let's just try to prove it then. So you're interested in Vy divided by V in 1. So Vy, which is at this point, divided by V in 1, which is at this point. So your resistance RT, this is equal to 1 over GM1. The resistance looking into the this particular source is going to be 1 over GM2, right? And then this is your RD2. Now we are trying to find out what is Vy. This is Vy over here, this point, that is your V out 2, that's a node Y, divided by V in 1. Now, if you think about it, that you have a 1 over GM1, if you have a 1 over GM1 resistance over here, and you have another 1 over GM2 resistance looking into this particular node. So what is the overall current that is coming out of your Thevenin equivalent voltage source and then flowing into the resistance over here, or flowing into the transistor? Because this resistance is RT, and then looking into the source of the M2 resistance, you again see some sort of a RS, like that, the source resistance looking into the M2. So the current that flows out of VT, current that flows out of this black box, is going to be VT divided by RT plus RS. What is equal to your RT? RT, we already found out, is equal to 1 over GM1. So this is the current, I. And what is equal to VT? VT is equal to V in 1. So I just replace VT as V in 1, RT as 1 over GM1, and RS, that is the resistance looking into the source of the M2 transistor, that would be 1 over GM2. Okay? So that's just the current that is flowing into the source terminal. And then your output voltage, that output voltage is going to be that current which will flow through the source terminal toward the drain side. It will be the same current because there is no current flow at the gate. So the source current is going to be equal to the drain current, and that drain current is going through the RD2 transistor and going to this AC ground, right? So what is going to be your output voltage, which is V out 2 in this case? The output voltage is going to be equal to RD2 times this current. And see, it's the same thing that we had done while we were solving homework number 6 as well. That if you have this common gate stage, look at the current that is coming in, and that same current which is coming in through the source terminal will be flowing at the drain terminal. Multiply that current with the resistance at the output or the drain terminal, and you'll get the voltage out through Ohm's law. So RD2 times I is going to be your V out 2. So what is I? I is V in 1 divided by 1 over GM1 plus 1 over GM2. So what you're interested in finding out is what is my V out 2 divided by V in 1. V out 2 is equal to your Vy. So that is going to be your RD2 divided by 1 over GM1 plus 1 over GM2, right? Because I'll just replace this I over here, and then I have RD2 multiplied with V in 1 divided by 1 over GM1 plus 1 over GM2 as my V out 2. So I take the ratio of V out 2 divided by V in 1. That's going to be RD2 divided by 1 over GM2 plus 1 over GM1. So that's my voltage available at the Y node or the V out 2 node. Now, the overall voltage gain for V in 1, that would be equal to Vx minus Vy. So you already found out what is your Vx that you found here. That my Vx is equal to V in 1 multiplied with this quantity. And then in the next slide, you found out what is going to be your Vy, and Vy is going to be V in 1 multiplied with this quantity. What is my overall differential output? That is Vx minus Vy. That's the definition of differential voltages. Vx minus Vy due to V in 1. Vx minus Vy due to V in 1 is going to be the value of Vx minus the value of Vy, whatever you had got from these two equations. So Vy is equal to V in 1 multiplied with Rd divided by 1 over Gm2 plus 1 over Gm1. Here you see you got the same thing. You just got minus Rd divided by 1 over Gm2 plus 1 over Gm1. So if you take Vx minus Vy due to V in 1, that's going to be minus 2 times Rd divided by 1 over Gm2 plus 1 over Gm1 times V in 1. Now, if your Gm1 is equal to Gm2 equal to Gm, then that will reduce to Vx minus Vy due to V in 1 equal to minus Gm times Rd times V in 1. Because you have 2 times Gm in the denominator, and the numerator you have 2 times Rd. So the 2 gets cancelled out, and you have minus Gm Rd times V in 1. Now, by symmetry, you can find out what would be the effect of V in 2 at node X and Y. That would be identical that of V in 1 with reverse polarities, because V in 2 just has a reverse polarity as compared to V in 1. So Vx minus Vy due to V in 2 is going to be plus Gm Rd times V in 2. And then if you add these two results due to your superposition principle, you can find out what is Vx minus Vy total divided by V in 1 minus V in 2 total. And that's just going to be minus Gm times Rd. And this is an expected result, right? We already discussed in the last lecture that if you have a differential circuit, and if the two branches are identical, the left side branch equal to right side branch, it's basically as if you can consider it as a half circuit and find out the gain for one half of the circuit. And the gain for one half of the circuit is just the gain of the common source amplifier. That's just Gm times Rd or minus Gm times Rd. So it's the same expected result that we got after applying superposition and then adding the voltages and so on, that eventually your gain is equal to minus Gm times Rd. That's it. Now, another way of thinking about it is something that we already talked about, that you can, if the left side and the right side are exactly identical, you can consider something called a half circuit concept. That if D1 and D2, let's say these are two black boxes that I have, considering one half of the differential circuit 1 and the second half of the differential circuit, that's D2, they represent any three-terminal active device. It doesn't need to be one single MOSFET. It could be maybe 5 different MOSFETs on the left side and 5 different MOSFETs on the right side. As long as they are identical, you can consider only one half of those. So if V in 1 and V in 2 are changing differentially from V0 to V0 plus delta V in and V0 to V0 minus delta V in, and if the circuit remains linear, that means if the circuit remains in saturation. What does linear mean? You know that linearity means that your output and input is represented with a straight line. So yeah, I didn't draw a straight line, but let's say if I had drawn a straight line, maybe something like this. So you have your V out and you have your V in. If your output and input are related by this straight line, then you say that the circuit is linear. Now, when does the circuit will remain linear? If the slope of this curve is equal to constant. What is the slope of this curve? It's gain. V out over V in, that is the slope of this curve, that is equal to your gain. And if gain remains constant, that's when you say that your circuit is linear. Now, you can argue that, yeah, I always expect my gain to be constant, but generally, the gain remains constant if the circuit is in saturation. As soon as the circuit goes out of saturation, the gain does not remain same. It does not remain constant. Or it basically drops and eventually goes to zero. That is the reason why you have to make sure that the transistors are in saturation. And if that happens, in that case, Vp does not change. This point Vp, the voltage at this point does not change. Why do I say that? Again, let's just try to understand this from another point of view. Let's say I have a sine wave on the left side and I have a 180-degree phase shifted sine wave on the right side. If I am applying both of them at the same time, and that's the assumption, right? That your V1 and V2 are differential. Then because of this V1, because of the V1, what should be the voltage at point P? And remember that if this is a, let's say, a NMOS over here, and then again another NMOS over here. So if I'm trying to look at this point P, and my input was V1, then at point P, I should see the same voltage because it's just a source follower. I'm applying my input at the gate, and I'm trying to look at my output at the source of that NMOS, right? So at point P, I should see the same sine wave as V1. But at the same time, I'm applying a V2 on the other transistor, this right-hand side transistor. And I should expect at the source of that transistor, the same voltage that you're applying at the gate of this V2, right? So at the terminal P, this so common source terminal, you should also see the negative sine wave at the same time. So now apply your superposition principle. You have the positive sine wave on the gate on the left side, and you have the negative sine wave on the gate of the right side. Now at the source, the common source of those two transistors, you have both the positive sine wave and the negative sine wave at the same time. When you add the positive sine wave and the negative sine wave, what do you get? You get zero, no AC. So this point P has zero AC voltage. Just because of the fact that you have a source follower action happening on the left side branch and another source follower action happening on the right side branch. So the point P, this midpoint over here, has zero AC voltage. That is another way of saying that this is AC ground. So in a differential circuit, that common point between the left side and the right side branch, that is going to be a AC ground if your V1 and V2, they are exactly differential versions of each other. Now, if they're not exactly differential versions of each other, let's say I have a larger amplitude sine wave on the left side and a smaller amplitude sine wave on the right side, then they will not cancel each other at the P terminal. And in that case, this will not be a virtual AC ground. But if the circuit is fully differential, if it is exactly identical D1 and D2, and if the input voltages are exactly identical, just 180-degree phase shifted from each other, then this common point is going to be connected to AC ground. Just intuitively, we didn't do any math, but intuitively, because you know how source followers work, you are just adding the effect of the two source follower using superposition principle. And that tells you that the voltage at this point is going to be zero. That's a very interesting observation, because what that tells you is that when you are doing the AC analysis, you just consider this part. You don't even have to consider the right side half circuit. Also, you don't have to consider whatever is connected here, because this point is already grounded. So this is referred to as your half circuit concept. But remember, the half circuit concept, in that the point P getting connected to AC ground, that concept is valid only if you have an exact differential version of the signal on the two sides. If they're not exactly differential, that is one has having a higher amplitude, or you're not having exactly 180-degree phase difference, then this concept is not valid. Then you'll have an AC signal at point P, and you have to consider the effect of that AC signal at point P. But then again, that's a more complex analysis. In this class, we are looking at more and more simplifications, which means that we'll just consider the fact that this point P is connected at ground. Okay. Now, if you do that connect point P to ground, so your circuit, the left side circuit, which is your original differential amplifier, that becomes this. Right? That the source of this M1 and M2, both of them are connected to ground. So you basically have divided the differential circuit into two parts. One is a common source on the left side, the other one is a common source circuit on the right side. And that's it. And now you can analyze only half of that circuit, either the left side or the right side, and you already know that the gain of each of those branches is going to be GM times RD. And that's what you found out by applying superposition principle in the previous discussion. So even without doing any math, now you can intuitively say that the gain of my circuit is going to be GM times RD. So this is the same result as in method 1. All right, so I think there are some more details over here for differential circuits, which are more complex analysis. So if you are interested in knowing about differential circuits in more detail, you can do that. But what I'm going to do is going to start discussing about the summary of these differential amplifiers, which will eventually lead us to the discussion on op-amps. So remember, we started this course looking at op-amps, and then we looked at non-idealities of op-amps. Then I asked the question that why are there non-idealities in the op-amp? And then my hand-waving answer was because there are MOSFETs and BJTs and diodes, these things can be there inside the op-amp. And because MOSFETs, BJTs, or diodes, they are themselves non-ideal, your op-amp is also going to be non-ideal. That was a hand-waving answer. Why? Because I did not explain how MOSFETs work. But now that you know how MOSFETs work, how all these different circuits work, we want to go back to op-amps and then try to design an op-amp from scratch using what we have learned till now. And that is basically going to be the last thing, or the second last thing that we learned in this course this semester. The other thing that is remaining is a little bit of understanding of digital circuits, on which I have already uploaded those 2 lectures, but we'll go through them once again next week. Now, differential amplifiers, this is again, you can consider this as a cheat sheet, the differential amplifier summary, which is also uploaded on your canvas. So you have differential amplifiers and then differential amplifier summary. So this is basically your cheat sheet on differential amplifiers. And I'll be talking about everything that we have learned in a very intuitive manner. So let's just start with the fact that in a differential amplifier, you want your input to be differential and you want your output to be differential, right? So your V in 1 is equal to minus V in 2. That is, if I have this positive sine wave or positive half cycle of the sine wave first and the negative half cycle of the sine wave later in V in 1, at V in 2, I'm going to have the negative half cycle first and then the positive half cycle. So you can write V in 1 equal to minus V in 2 because they are 180-degree phase shifted. Let's just say that is equal to V in. V in 1 equal to minus V in 2, that is equal to V in. The output is also going to be differential. It's just an amplified version of each of those because you already know that this point Vp is a virtual ground. So this point is a virtual ground. So the left side can be considered as a separate common source amplifier. The right side is another common source amplifier. And the output is just GMRD times this input. And this output is also GMRD or minus GMRD times this input. So, and if you take the difference of the 2 outputs, Vout1 minus Vout2, that is going to be your overall Vout. But your Vout1 is equal to your minus Vout2. Let's say that is equal to Vout. So your differential mode gain, ADM, A substitute DM is signifying the differential mode gain. That is equal to Vout1 minus Vout2 divided by V in 1 minus V in 2. Because your Vout1 and Vout2 are 180-degree phase shifted versions of each other, Vout1 minus Vout2 is going to be twice Vout. Similarly, V in 1 minus V in 2 is going to be twice V in. So your 2 gets cancelled out. So differential mode gain is nothing but V out over V in of each of the branches. So that makes life a lot easier, right? It's just V out over V in of each of the branches. Of course, one important point is that your VP is a virtual ground. But VP is a virtual ground only if your V in 1 equal to minus V in 2. If V in 1 is not equal to minus V in 2, if they are not 180-degree phase shifted versions of each other with the same amplitude, in that case, VP is not a virtual ground. So that's just a condition. But in this class, we'll always consider your V in 1 and V in 2 are 180-degree phase shifted versions of each other. That means VP is going to be a virtual ground. Now, there is also another concept called common mode gain, ACN. A subscript CN is common mode gain. And what does that say is that if you have an AC V in, let's say instead of connecting these differential mode inputs, V in 1 and V in 2, let's say you connect V in 1 and V in 2 together. You short V in 1 and V in 2, and then provide a AC voltage V in. Let's say I apply just one AC voltage V in by shorting the two inputs together. Now, ideally, what should we expect? What should we expect at the output? What should my V out 1 minus V out 2 be if my V ins are connected together? Of course, they are equal, which means that my ideal input that I'm providing is equal to 0. V in 1 minus V in 2 is going to be 0. That means V out 1 minus V out 2 should also be 0. But again, that's what ideal differential amplifier will tell you. In real life, the differential amplifier will also be non-ideal. Why? Because the GM of these two transistors, let's say this is GM1 and this is GM2, they may not be exactly equal, which means that the current they create over here and over here, those two currents are not equal. If those two currents are not equal, they do not cancel each other out. That means this point VP is not at AC ground. Similarly, this RD1 and RD2, they may also not be equal to each other. There could be a small difference in RD1 and RD2. And the current itself is not equal on the left side branch and the right side branch. So when you multiply a non-equal current with a non-equal resistance and take the difference of the two, you may not get 0. Right? What is this, the voltage drop across, or V out 1? V out 1 is basically this current that is flowing in the left side branch multiplied with RD. V out 2 is the current that is flowing on the right side branch multiplied with RD. Now, in a real scenario, the RDs are not equal. RD1 is not equal to RD2. The current that is flowing on the left side branch is not equal to the current on the right side branch. It's fairly similar, but not exactly equal. Which means when you take V out 1 minus V out 2, that will not be 0. So even if your V ins are connected together, and ideally your output V out 1 minus V out 2 should have been 0, in a non-ideal scenario or in a realistic scenario, you do not get a 0 out. Now, the ratio of your output to input in that case, when you're applying a common mode AC input, the ratio of the output AC divided by the input AC voltage is called the common mode AC gain. And remember, because we are talking about gain, we are still talking about AC signal. This common mode gain does not talk about any common mode DC gain. Even though we say that, yeah, common mode, whatever is common between the left side and right side branch, that's common mode, right? But whenever you're talking about gain, remember we talk about gain only in an AC sense. There's no concept of DC gain in this class because and you can actually have defined DC gain in a way that if you have a DC to DC converter in some, let's say, power electronics classes, and then you change one DC voltage level to another DC voltage level, you can define DC gain with respect to that. But in this class, whenever you are talking about gain, we are talking about AC gain. So your output is an AC quantity. The input is an AC quantity as well. The only difference is that the input AC quantity is common for both the terminals. So V in 1 and V in 2, they are shorted. And then we are calling that equal to V. So when V in 1 equal to V in 2, they're still AC, but it's the same quantity. Then the ratio of your output to input is called the common mode gain. There is a concept of CMRR, common mode rejection ratio. Ideally, the transistor or the differential amplifier should have a very high differential mode gain. Again, if you think about an op amp, an ideal op amp has infinite gain for the difference of the two inputs, right? Even for an ideal op amp, we said that the gain output is equal to V1 minus V2 times A. At the output of the op amp, you expect A times V1 minus V2. See, that is very similar to what you saw for differential amplifier. So you already get a sense that inside my op amp, there is somewhere a differential amplifier. And most likely at the input side itself, because the two inputs, V1 and V2, they go to these gates of the two transistors, NMOS transistors. And you know that looking into the gate of the NMOS, you see infinite impedance. And you know that looking into the two inputs of the op amp, you also see infinite impedance, ideally. So you already get an intuitive sense that, yeah, this is going to be the first stage inside my op. Question? Yes. So if you are building a MOSFET-based circuit, now if you build it using BJTs, we haven't yet talked about BJTs though, but I'll be talking about them toward the end. So you have to apply a little bit of different strategy to make sure that the input is still infinite impedance. But for a MOSFET, that concept is pretty easy. You just have the gate at the input. That means you apply some sort of a differential amplifier at the input side, and that will make the input impedance infinite ideally. And then the gain of the op amp we already know is A times V1 minus V2. That's a differential mode gain of the op amp again. And we just talked about the differential mode gain of the differential amplifier as well, which are basically the same thing, same concept. And that is because there is a differential amplifier inside your op amp. Now, there is a concept of CMRR, or common mode rejection ratio. What does that mean? If you take the ratio of differential mode gain over common mode gain, and again, these are both AC gains. There's no concept of DC here. ADM is the differential mode AC gain. ACM is the common mode AC gain. So your input is a common mode in one case. The input is a differential mode in the other case. So CMRR is equal to 20 log base 10 times, or logarithm to the base 10 of ADM over ACM, absolute values. And that is defined as your common mode rejection ratio. Ideally, that should be infinitely large, because your differential mode gain for an ideal op amp or ideal differential amplifier should be infinite. Reality, it should be GM times RD, right? As you already know. But ideal op amp has infinite gain, so ADM should be infinite. Ideal op amp has zero common mode gain, so ACM should be zero. The ratio of those two should be infinite once again. Half circuit analysis, again, something that we had seen. We'll stop here, but let's just discuss the half circuit analysis. That you already saw this, that this can be drawn as this, because the node VP is a virtual ground, as it will see the left side Vin1 as well as the right side Vin2 at the same time at the common source terminal over here. So that's why this becomes a virtual ground. This current source over here is called a tail current source. In most literature, you'll see. And that's just a nomenclature, that whenever people talk about a tail current source, they're actually talking about this transistor or this current source over here. Because for a differential amplifier, if you think about this as some kind of an animal, let's say a mouse, then this becomes the tail of that animal. So that's why the nomenclature is like that. And the gain here is going to be minus GM times RO in parallel with RD. If RO is infinitely large, it's just minus GM times RD. Right? So everything that we learned today, that's what is summarized here. In the next lecture, I'll start with a little bit more complex concepts related to differential amplifier. Questions? Yeah. Yes. So you know that a MOSFET is basically a current source. If the MOSFET is in saturation, the MOSFET is a current source. Okay. So you can bias this MOSFET in saturation. So that will make it a current source. Or you have already learned about current mirrors. So you can mirror a external current and put it over here to a MOSFET, and then connect the drain and the gate of this MOSFET together. And that will make sure that the current flowing here is the same current that is flowing here if the W over L ratios of the MOSFETs are equal. So this is the way people actually implement this. Because again, if you are talking about voltage biases, voltages can always have noise, or it can have IR drop. Because if, let's say, I'm connecting a voltage source, let's say I don't have this. Let's say I don't have this left side circuit, and I'm connecting a voltage source over here. There is some amount of leakage, like there is always, even though, let's say we say that there is the resistance looking into the gate is infinitely large, but there is always some amount of leakage through the gate. So that means there is some amount of small current through the gate, and then this path will have some amount of resistance. That means if I'm applying a voltage, let's say 500 millivolt here, what I may see at the actual gate of the transistor may not be 500 millivolt. It could be something different because of the voltage drop on this resistance, which is just the line resistance or the wire resistance. That is why instead of applying a voltage source, people like to use a current source, as I had shown earlier. Let me just redraw it back again. That you have a current source here, you have a transistor, you connect it in a fashion similar to the current meters, and then whatever current is flowing here will be the same current that is flowing here, irrespective of the resistances. Right? If the lines or the wires themselves have resistances, it doesn't matter. The left side current still has to be same as the right side current. And that's why you generally bias circuits with current mirrors or current source instead of biasing them with voltages. Although voltages are easier to think when you are doing the analysis, but in real life, if you're building a chip, you'll most likely use a current source to do the mirroring or the biasing. Okay. So let's stop here. In the next lecture, we'll take a look at more interesting details of the differential amplifiers. And that will basically lead us to the discussion on op amps, that how to build an op amp using everything that we have learned in the course.